Assalamu alaikum. So we meet again to learn operating systems. I hope you are enjoying this content. Let's start lecture 5. We start a new chapter today called Uniprocessor Scheduling. Please refer to chapter 9 of the book by William Stallings. Let's revise a few important points. A multi-programming system has many user processes in the memory at any time. A process is composed of CPU bursts in which it runs on the processor and IO bursts in which it asks for an IO transfer and then waits for its completion. The idle time of the processor is reduced by assigning the processor to a ready process when the currently running process blocks for IO. Scheduling means selecting a process out of a pool of processes. The key to multiprogramming is scheduling. Every time the currently running process leaves the processor, the operating system needs to select another process. Scheduling needs to be done with the least delay or latency. The time spent in selection contributes to the idle time of the processor because the processor sits waiting for a decision over who is going to run next. There are four types of scheduling: long-term scheduling, medium-term scheduling, short-term scheduling, and IO scheduling. Here, the first three types are processor scheduling. The last type relates to IO and will be covered in another chapter. Let us look at the three types of processor scheduling. The aim of processor scheduling is to assign processes to a set of processors in such a way that optimizes system response time, which is the time taken by an interactive system to generate a response to the user, system throughput, which is the number of jobs processed by the system in unit time, and system efficiency. Efficiency is the ratio of useful work to resources expended. The resources are processor and memory. In other words, the ratio of the output to the input of a given system is efficiency. We will focus on uniprocessor scheduling. When there are many processors in the system, the challenges of scheduling are magnified. We must make sure that two processors do not select the same process for execution. We must also ensure that no process keeps waiting to be selected in a multiprocessor system. The scheduling activity in a system is broken down into three separate functions: long-term scheduling, medium-term scheduling, and short-term scheduling. The long-term scheduler decides, is there a need to add a new process to the system? If yes, which program should be translated into a process? In a batch system, the user submits a batch of programs. In an interactive system, the user commands the computer to execute several programs. The LTS converts a program into an executable process using an algorithm that may be based on fairness, priority, expected execution time, or IO requirements. So, we can have an LTS that works on first come, first served basis. This is a fair thing to do. We are not favoring anyone. Whoever comes first is admitted first. On the other hand, we can be partial to some processes. This is done using priorities. We assign a priority label to each program. A higher priority program is admitted to the system before a lower priority program, even if the lower priority program came first. If we have predicted execution times for each program, we can either admit long jobs first or short jobs first. If we know the IO requirements of programs beforehand, we can admit programs with fewer requirements first. Remember CPU intensive and IO intensive jobs? If the LTS knows the character of each job as either CPU or IO intensive, it may attempt to keep a balanced mix of jobs in the system so that performance improves. LTS controls the degree of multiprogramming. Do you remember what the degree of multiprogramming is? It is the number of processes in the memory at any time. If the degree of multiprogramming falls, we have a system with very few processes. So there is a chance that those processes will all become blocked. The processor will sit idle. Our precious computational resources will go wasted. When degree of multiprogramming falls, the LTS starts creating processes to increase the number of executable choices for the processor, reducing processor idle time and wastage of resources. Whenever a process exits the system, the LTS considers if a new process should be injected into the system. If processor idle time exceeds a threshold value, the LTS may be invoked. The medium-term scheduler decides which process is to be swapped in or out of the memory. Medium-term scheduling is part of the swapping function. This decision may be made when main memory becomes free. The system would require swapping in of some processes. This decision may be made when main memory becomes full. The system would require swapping out of some processes. When MTS is called to swap out processes, it is reducing the degree of multiprogramming. This helps when our processes ask for more memory. We can swap a few processes out, free up some space, and then expand the address spaces of the processes still sitting in the RAM. MTS considers the memory requirements of the process and the currently available memory. It can also make decisions based on priority. The short-term scheduler decides which process should be given the processor. The short-term scheduler is called at the expiry of each time slot. Even during a time slot, if a process blocks, the short-term scheduler is asked to select another process. During a time slot, if a process makes an operating system service call, the STS is asked to select another process for execution. Here, I need to tie the new term with the old one. The short-term scheduler is the dispatcher. The STS may decide fairly or it may use priorities. If it selects the process which came first, it is fair. If it selects the process with the highest priority, it is being biased towards a set of processes. The decision to put a newly created process in the RAM or the hard disk is a long-term scheduling decision. The decision to bring a process from the hard disk into the RAM is a medium-term scheduling decision. The decision to assign the processor to a process in the RAM is a short-term scheduling decision. Now tell me, which scheduler will be called most frequently? You are right, the short-term scheduler. It is called short-term because the decision spans a short period and it is required to be made again and again. So the next question is, which decision is the next most frequent decision? If your answer is the medium-term scheduler, you are right. The least frequent decision is that of the long-term scheduler. Long-term scheduler is called when we want to add a new process to the system. Once the LTS has created a process, if it is in RAM, it is part of the input to the short-term scheduler because it is ready. And if it is on disk, it is part of the input to the medium-term scheduler because it is ready suspended. In this diagram, we see the working of the three schedulers with the different queues in the system. The short-term scheduler has one queue to select from, the ready queue. A process may come into the ready queue because the long-term scheduler placed it there after creation. It may come into the ready queue because the IO event it had been blocked for has completed. It may come into the ready queue because its time slice has expired and it has been kicked off the processor. The medium-term scheduler selects a process from either the ready suspend or the blocked suspend queue and moves it to the ready or the blocked queue. So the medium-term scheduler is swapping processes in and out to meet memory requirements of all processes and to optimize system performance. The long-term scheduler adds processes to either the ready or the ready suspend queues. This picture only shows the long-term scheduler adding processes to the ready queue, but we know that the long-term scheduler can add a new process to the ready suspend queue too. Now that we have understood what uniprocessor scheduling is, let us take a look at the different algorithms that exist for uniprocessor scheduling. We are now focusing on short-term scheduling. The main objective of short-term scheduling is to allocate processor time in a way that optimizes some aspect of system behavior. We can use system-oriented or user-oriented criteria for STS. User-oriented criteria relate to system behavior as perceived by user or process. These are things that matter to the user and make the user love or hate the computing system. System-oriented criteria focus on effective and efficient utilization of the processor. These are things the designer of the system wants to see in it. User-oriented criteria are important in virtually all systems. System-oriented criteria are not very important in uniprocessor systems. STS criteria can be those related to performance and those that are not directly related to performance. Performance generally refers to the speed of the system. Performance-related criteria are quantitative and can be measured, while those not related to performance are qualitative and difficult to measure. The different STS criteria that we are going to talk about are turnaround time, response time, deadlines, predictability, throughput, processor utilization, fairness, enforcing priorities, and balancing resources. The delay between submission and completion of a process is called its turnaround time. This period includes time spent waiting in a ready queue for selection and the actual execution time. Batch systems use turnaround time as their performance measure. A good system has small average turnaround time. This is a user-oriented measure as it matters to the user. The user will be happy with small turnaround times and frustrated with large turnaround times. This is a performance-related measure. A fast system typically has small average turnaround time, which can be measured. The delay between submission of a request and arrival of the first response from the system is called response time. You are sitting at a terminal and you issue a command to do something. There is a wait. Then the system asks you to verify yourself. This is its first response. Your request has not been fulfilled yet, but response time is measured from the time of issuance of command to the first reply of the system. This period includes time spent waiting in ready queue for selection, time taken to generate the first response for the user. Note that the execution of the request is not complete yet. Interactive systems use response time as their performance measure. A good system has a small average response time. This is a user-oriented measure as it matters to the user. The user will be happy with small response times and frustrated with large response times. This is a performance-related measure. A fast system typically has small average response time, which can be measured. Deadlines. The scheduler selects processes in a fashion that maximizes the percentage of deadlines met in the system. If I select task A first, I will be able to complete tasks A and D within their deadlines. But if I select task B first, then I will be able to meet the deadlines of A, B, and C. So I will select task B. Real-time systems use deadlines as their performance measure. These are systems in which even the correct output becomes useless if its deadline is not met. Consider that an ICU has a patient in critical condition. There is a computer monitoring his heartbeat. The computer must generate an alarm at the nurse's station if the patient's heartbeat becomes abnormal. Suppose that the patient develops complications. His heartbeat fluctuates. The computer detects this, but instead of sounding an alarm within a few seconds, it generates an alarm after 15 minutes. By then, the patient is dead. The system works fine, generates the correct output, but misses the deadline. So even the correct output is of no use now. Instead of generating this alarm at the nurse's station, it should be generated to call the guy who bathes dead bodies. This is an example of real-time system. A good system meets a large percentage of its deadlines. This is a user-oriented measure as it matters to the user. The user will be happy with all deadlines met and frustrated with most deadlines missed. This is a performance-related measure. A fast system typically meets a large percentage of its deadlines. We can calculate the percentage of deadlines met and deadlines missed. Students, now I want you to pause the video, open a Word file, save it as my roll number underscore lecture underscore 5 and write the answer to this task. An unmanned spacecraft moves over Mars' surface while a camera on board captures images. Every few minutes, people on the ground station request a picture of its current location to be sent. Which type of system is it? Batch, interactive, or real time? And do tell me why. Predictability. A system is predictable when it runs a job in the same amount of time and at the same cost, irrespective of the load of the system. Let us consider a bakery selling cupcakes at the rate of 20 rupees for one. Some days, there were no customers at this bakery. On other days, it would be full of people waiting to buy cupcakes. But the price remained the same. So no matter which day of the week I went to get cupcakes, I got them at the same price. This was the situation before the COVID-19 crisis. When lockdown started, the bakery closed up. The owner of the bakery lived next door to his shop. When he would see five or more customers standing outside the shop from his bedroom window, he would open the shop shutter just a bit and sell cupcakes at 20 rupees per piece. But if there were four or less customers, he would not open the shop. I would loiter outside his shop. I would see his face in the window. But as I was the only person standing, the shop would not open. After 2 or 3 weeks of lockdown, he started opening the shop shutter for one or two customers too. But he sold the cupcakes 50 rupees per piece. During lockdown, there was no guarantee that the shop would open, and there was no guarantee that I would get the cupcakes I crave or that I would get them at a suitable price. Life became unpredictable. If a system has a wide variation in response time or turnaround time, it is unpredictable. Consider a restaurant. If you go when there are very few customers, you are served your order in 15 minutes. But if you show up when the restaurant is packed with people, it takes an hour to catch the first glimpse of your ordered food. This restaurant is unpredictable. Eat somewhere else, or even better, eat at home. Stay safe. A good system is predictable. That is, no matter what the workload, the system takes the same delay to serve a customer. This is a user oriented measure as it matters to the user. What are the adverse effects of unpredictable systems? Users do not trust them. Users always opt for predictable systems. This is not a performance related measure. We cannot measure how predictable a system is. Fast systems may be predictable or unpredictable. Speed has nothing to do with predictability. Throughput. The number of processes completed per unit time is the throughput of the system. It is a measure of the amount of work performed. The scheduler aims to optimize system utilization, and this increases the throughput. We like systems with high throughput. Restaurant A services 5 customers in an hour. Restaurant B has the same number of waiters and cooks but services 7 customers in an hour. Obviously, the better system is Restaurant B. This is a system oriented measure as it matters to the system designer or the implementer of the system but not the user. As a customer, I don't care about the throughput of the two restaurants. It matters to their owners because restaurant B owner clearly earns more than the owner of restaurant A. I just care about the quality of food and the time they take to serve me. This is a performance related measure. A fast system typically has high throughput, which can be measured. The percentage of time the processor is busy is called processor utilization. The scheduler aims to optimize processor utilization. If a system is expensive and shared among many users, this criterion matters a lot. Suppose CIS department invests ₹1 million in a supercomputer for its PhD students. The chairman would be extremely unhappy if he has only 2 students enrolled in the PhD program because his very expensive machine is being used scarcely. But if 15 people are doing PhD in the department simultaneously, the chairman will consider the ₹1 million well spent. In single user systems and real time systems, throughput is not very important. If there is a machine that only I use, I know it is going to be underutilized most days. My father gave me this laptop a few years ago, but I am using it night and day only now for the online semester. Before the lockdown, it was scarcely used. And I do not mind this fact because what matters most is that I have a laptop to use when required. In a real-time system, I don't care if the system is not used most of the time. It should be functional when the need arises and meet its deadline. In our critical patient example, the system normally does not generate any alarm because patients get better and move out of the ICU. But if someday someone has a cardiac problem, it is important that the system raises the alarm within seconds. So we do not worry for underutilization of the system generating the alarm. This is a system-oriented measure, as it matters to the system designer or the implementer of the system, but not the user. A PhD student does not care how much the supercomputer is utilized. He only feels happy that the department has got the supercomputer for him. The department is concerned that the supercomputer is used as much as the money invested in it. This is a performance related measure. A fast system typically has high processor utilization, which can be measured. If a system treats all processes in the same way, it is a fair system. I call you to an online session. I answer all queries as I receive them. This is fairness. In another session, many students ask questions. One of them is Ali. I note all the questions down. Then I answer Ali's query first. After this, I answer all questions. Now, do you think I am fair? A fair system is impartial or unbiased. Fairness is a system-oriented measure, as it matters to the system designer or the implementer of the system, but not the user. The user does not care if a system is fair as long as he gets his job done. This is not a performance related measure. We cannot measure how fair a system is. Fast systems may be fair or unfair. Speed has nothing to do with fairness. Enforcing priorities. Processes in a system have been assigned numbers that signify their priority. For example, a process assigned the number 9 has higher priority than that assigned the number 3. If a system is biased towards a set of processes, the system is priority driven. In my second session, many students asked questions. I noted all the questions down. Then I answered Ali's query first. I have assigned a higher priority to Ali than the rest of the class. So to enforce that priority, I answered all other queries after answering Ali's query. If a system is priority driven, then it is necessary that it always remains that way. What I want to assert is that priorities must not be violated even for a second in a priority based system. A priority driven system is partial or biased or unfair. Priority enforcement is system oriented, as it matters to the system designer or the implementer of the system, but not the user. The user does not care if a system is using priorities as long as he gets his job done. This is not a performance related measure. We cannot measure priority enforcement. Fast systems may or may not be priority driven. Speed has nothing to do with priority enforcement. Balancing resources. If the system selects processes in a way that all resources are kept busy, the system is balancing resources. Processes that will ask for resources that are currently underutilized are favored. Consider there are two doctors and a nurse at a hospital. One of the doctors is very experienced, the other is a fresh graduate. Then Corona hits the world. One day during lockdown, the hospital receives lots of patients. The doctors and the nurse decide that they will attend to the patients together. The incoming patient will be directed by the doorman to whoever is free. So if both doctors are busy, the incoming patient moves to the nurse, who checks his temperature and other vitals. The system works in such a way that all three of them are equally loaded. This is resource balancing. This criterion includes all three forms of processor scheduling. LTS inducts processes who will ask for lightly loaded resources. MTS sweeps processes who will ask for lightly loaded resources into the RAM, swapping others out. STS gives the chance of execution first to the process who will ask for lightly loaded resources. Resource balancing is a system-oriented measure as it matters to the system designer or the implementer of the system but not the user. The user does not care if a system is balancing resources as long as he gets his job done. This is not a performance-related measure. We cannot measure resource balancing. Fast systems may or may not balance resources. Speed has nothing to do with resource balancing. This table provides a summary of what we have been talking about in the previous slides. All criteria cannot be met in the same system. For example, a priority-based system is not fair. Or to improve response time, we use a small time slot in time sharing systems. This leads to a lot of switching between processes. As we take some time to switch from one process to another, switching overheads increase. This brings down system throughput, good response time, bad throughput. See what I mean? We can only choose one criterion and optimize the system around it. And now it's time for the second task. The CIS department supercomputer selects teachers' jobs before students' jobs. Among teachers, it favors those with greater experience at the department. It treats all students of the same semester fairly, but when two students are in different semesters, it favors students who have passed more semesters. SN means student in the nth semester. Also, the senior most teacher in the department is Sir Shahab Tehzeeb. Sir Kashif Asras is senior than Miss Ibshar Ishrat and junior than Mrs. Maria Waqas. Jobs are submitted in this order: S4, S5, MW, which stands for Maria Waqas, S3, S4, II, which stands for Ibshar Ishrat, S2, S2, S8, ST, which stands for Shahab Tehzeeb, S1, KA, which stands for Kashif Asrar, S3. What is the order of execution of these jobs? Let us now see how priorities are enforced in a system. A system has n plus 1 priority levels from 0 to n, 0 being the highest, n being the lowest priority level. In this example, the smaller number represents a higher priority. This convention is used in Unix. Windows has the opposite convention, as a larger number represents a higher priority. Coming back to our system, each priority level has its separate ready queue. A process is added to the tail of the ready queue that corresponds to its priority number. When the dispatcher is invoked, it first checks the ready queue corresponding to priority number 0. If a process is present there, it is selected for execution. If RQ0 is empty, the dispatcher checks in RQ1. If RQ1 is empty, the dispatcher checks in RQ2 and so on. Now suppose that two processes enter this system, A is added to RQ0, B is added to RQ5. The dispatcher obviously selects A. Now, C and D are added to RQ1. When the time slot of A expires, the dispatcher will select C. When the time slot of C expires, it will select D. Now suppose that the system receives a steady stream of processes with priorities 0, 1 and 2. What will happen to B sitting in RQ5? It was one of the first two processes to enter the system. Will it ever get selected? Do you feel bad for B? What is happening to B in our example is called starvation. When there is a steady supply of higher priority processes in the ready queues, low priority processes wait for long periods of time for selection. We say that the low priority process is starving. Starvation occurs when a low priority program is requesting for a system resource but is not able to execute because a higher priority program is utilizing that resource for an extended period. No process should suffer starvation. Starvation only happens in unfair systems, never in fair systems. A fair system does not favor anyone. All priority based systems are unfair. This means that starvation can occur in all priority based systems. Can starvation be overcome? Yes. We can change the priority of a process with age. This is called aging a process. Suppose we have a system with 5 priority levels from 0 to 4. 0 is the highest priority level. A process called X is in RQ4. We age the process by advancing its priority level after every 5 seconds of wait. So when X has waited for 5 seconds, it is moved from RQ4 to RQ3. After another 5 seconds, it is moved from RQ3 to RQ2. After another 5 seconds, it is moved from RQ2 to RQ1. As X moves up in the ready queues, its chances of selection keep increasing. The aging mechanism favors processes with long waiting times. The more you wait, the higher priority you achieve until you finally execute. In this lecture, we elaborated on the three types of processor scheduling. We talked about various scheduling criteria and discussed examples that were relevant to them. We understood the queuing mechanism that enforces priorities, and we defined and explained starvation. Finally, things to do. Read the book, class. And when I asked you to submit your task file, do it in Google Classroom. Write your questions on a piece of paper and keep it in front of you during the online session. If you have suggestions relevant to the content or quality of this lecture, email them to me. Take care of yourself. I'll see you soon. Allah Hafiz.